So, we are at lecture 2 of our recorded video series, and today is Wednesday, the 18th of March. So this is number 2. I sent an email this morning to the class about the schedule to everybody, and we're going to stay on our schedule here, just the way your handout shows, with each lecture. I think there's 12 lectures left, maybe 11 after today. And we'll do those at the normally recorded times, and we'll do the exam next Wednesday. At that recorded time, I'll email that to everyone, and you have 24 hours to work it in, get it back in. So stay tuned, watch your emails for updates, because there'll be more emails now because there's less in-class work. Last time, we got into modeling yield, and I left this up there from last time, and we got into the 3 types of photosynthesis. So today I want to follow that up in more depth. And I keep showing this, that's the whole biochemistry, which that's not even a handout. But let me quickly review C3C4 CAM. And let's put the C3C4 part right here. A giant stomate, really giant, because the bigger you draw it, the easier it gets to understand. Then CO2 coming in here by diffusion through the stomates. On this side, we have C3 photosynthesis sucking it out to carbohydrate by rubisco. One enzyme sucking it out. Over here, this is like 2 wrestlers, I guess. In this corner, we have rubisco, which is sucking it out using PEP carboxylase, which is such a powerful enzyme. So really, this arrow, we could draw a whole bunch of arrows here for PEP carboxylase. This is a fundamental advantage, and it means you can run the stomates more closed because it's got such a good pump. But then, of course, as you know, this still needs rubisco. And so this only helps when we have low CO2 inside the plant. So with this little diagram, we can make a little review of advantages. And let me put the advantages over here. C4, the one big one, let me get a better, better marker here. Water use efficiency, WUE. I won't spell that out because we've had it up here lots of times. It's really obvious that C4 are fundamentally more water use efficient because with all this suction for CO2, C4 plants can run with the stomates more closed. They've got a vacuum cleaner for CO2, and when those stomates are more closed, less water comes out. That's a big difference in those two. The water use efficiency of C3 plants is about, these are round numbers, 1 gram of biomass per 600 grams of water. Now this is 600 mils of water. Think about that. That is just astonishing. A paper clip weighs about 1 gram, and this is more than 1/2 liter of water. That's how much water comes pouring out of the stomates in order to get CO2 in. Now let's look at C4. Because now they can do 1 gram per about 300 grams. of water. C4 fundamentally cut the water use in half, all other things being equal. It's a huge advantage given that we're going to run out of water. And it's all because of that enzyme and that diagram right there. Now let's look at CAM. Since we're on water use efficiency, what do CAM do? Open their stomates only at night. And then store all the malate in the day, open their stomates at night to get more CO2 in. And this is a little like somebody kind of holding their breath all day and then breathe at night when it's cool. I mean, it's a hard thing to do, but CAM plants can do it. Let me draw over here. It's way over here. Remember these two lines are our venerable psychrometric chart. And here's absolute humidity, ABS, humidity, and as you know, and can do only very well, here's daytime. Let's say this is 25 degrees C, and here's the vapor pressure deficit for daytime. This is what both C3 and C4 are working against, a huge vapor pressure deficit. Now look at CAM. Boom! They open their stomates at night, and when it's cool, I'm just going to put in here 15 degrees C. This is the vapor pressure deficit that CAM are working with. And not only is the vapor pressure deficit small, but in the day over here, if you're out of water, the leaves heat up and they go up here, so you end up with an even greater deficit. And guess what? CAM at night, the leaves are often below the air temperature. So wow, this gradient for CAM can be just tiny at night. They're tremendously water use efficient, but that diagram we showed the last time where they have to fix malate in the day and then use that at night is a big, big penalty. But hey, if you're out of water, who cares how big the energy penalty is? You're out of water. That's the limit. Now let's put CAM up here. They're better, right? Because by the way, CAM have the benefit of C4 photosynthesis and the benefit of being able to open their stomates at night. So it's a double benefit. Here's CAM. As a rule of thumb, 1 gram per, drum roll, 80 grams of water. That's astonishing. So we're going to see more CAM plants. That's why they can live in the deserts. Lots of epiphytes that are in trees are CAM plants. They don't get much water. They're in a tree. They don't have roots in the ground. CAM plants are amazingly adaptable all over the place. They just grow slow. This is a handout that I'm going to give to you, send it electronically, and I call it Trade-offs in Plant Ecology, C3, C4 CAM, and I talk about efficiency. So water use efficiency is huge. Now I ought to put this in a different color. There are another limiting factor in all ecology and all plant production is nitrogen. How do these 3 plants use nitrogen? Equal, right? Wait a minute. C4 have 2 enzymes. Rubisco takes a lot of nitrogen. Something like half of the nitrogen in plants is in Rubisco. It's an amazingly hungry enzyme for nitrogen. C4 have both Rubisco and PEP, so wouldn't that tell us that C4 is bad news? It's going to take extra nitrogen? Turns out that's wrong. Here's why it's wrong. If we put N over here, I'm going to do N. This is a ton of nitrogen. in C4 plants, the pep is big and the rubisco is small. C4 plants don't need that much rubisco to operate because they're being spoon-fed by pep carboxylase. So this big enzyme up here, the end goes way down, and pep carboxylase is a low-end, lower nitrogen-containing enzyme. So it turns out C4 plants are more nitrogen use efficient than C3. So ecologically, that's a very big deal. But we got a Haber-Bosch process. We just pump oil out of the ground, make nitrogen, and put plenty of N on, so we can use C3 plants because we just fertilize them with N. So in agriculture, in ecology, this is a huge advantage. In agriculture, it's less so because we just fertilize them. So we put C3 more. Let me change this. Let's change this to nitrogen efficiency. C4 better than C3. That's a second big advantage of C4. What do we know about temperature? Temperature, is it C4 better above about 25 degrees C. So depending on temperature, depends on which one is favored. Consider that all of our crop plants, or not all, many of our crop plants are irrigated so they can be more light use efficient, and that makes the leaves cooler. So this advantage of C4 becomes less when you have irrigated agriculture because they evaporate water, cool the leaves, and they just don't get so hot. But if we run out of water, C4 is going to be better. So this, and then finally this handout that is coming, CO2. And I'm going to put this CO2 concentration, C4 better at low CO2. Now, the inverse of this is true. C3 is better at high CO2, but this is because of that double enzyme system to suck CO2 out of the air. But as we end up with higher CO2 on the planet, very gradually, C3 plants are starting to get favored over C4 because of more CO2. So, 1, 2, 3, 4. Water use efficiency, nitrogen efficiency, temperature, and then CO2 are the differences between these two. And as a quick general rule, CAM is sort of like C4 on steroids. I mean, it's an extreme version of C4 plants. This is what's described in this handout that I made for, I pretty much summarized it on the board. Trade-offs in plant ecology, coming soon to your email inbox. Now, this is the end of what I want to say about the types of photosynthesis. Now I want to segue into modeling yield, which we've already done, and I left it up here from last time to provide a link from one lecture to the next. Our 4-component model, when we do energy efficiency for each step. And using these numbers, we got around 1% for typical and 10% for potential. But we don't measure yield in percent energy efficiency, how do we measure yield? What's a high or a typical yield of any crop plant? If Wyatt was here, he would tell us the number for potatoes. He already told me the best growers in Idaho can get 600 sacks per acre of potatoes. But we won't go through potatoes, but we could. We calculate 600 sacks, pounds per sack, how much water's in the sack. What we're after, and we're going to modify this in a second, is a yield in grams per meter squared of ground area per day. It's not percent, we're going to get grams, and this is just units conversion, which I'll go to in a second. But first, what's a high yield? You guys, any of you know what high yield of some major crop, or typical yield? Years ago, when everybody came on farms, they knew exactly what their yield was for whatever crop they grew. I was anticipating this, so I have some graphs. I could scan these in, we can send them. There. Should I make this bigger here? Let's see. Here is, doesn't take long to type this up on the internet. Here is corn and wheat historical yield from 1870 to now, and long about right after World War II. What did we get right after World War II that made yields go up so fast? Fertilizer. We got Haber-Bosch nitrogen fertilizer, and then the genetics. Lots of attention to genetics. So boom, yields went up. Corn, this is not records, this is typical. 160 bushels per acre of corn. Let's put this up here. We can probably erase this now. Now we'll go into the whole thing. Corn. This is bushels, BU per acre, AC. 160 wheat, much less. We'll call that 40 bushels per acre. So there's some typical yields. Now, I'm going to give you a handout on units conversion in a second, because we want to get from these really bizarre units of bushels per acre to the Olympic size and weight, universal SI units, grams per meter squared, and more importantly, grams per meter squared per day. But I think you could all look up the numbers and make the conversions. But let's first look at some other yields. Let's see. Take this off. Oh, that's a little too big for this graph. Hold on. There. Is that focused? Pretty good, pretty good. Yields, rice yields in China and Japan since 1960. Now we're getting up, and the lines are going up. They're not going up as fast as they used to. You can't see this in the, this is 2020. This unit right here is tons per hectare. That's how the world measures yield, tons per hectare. So let's put that up here. Rice. And that number is 5. If you can see it right here, that's a 5 tons per hectare. So 5 tons, and HA is hectare. So neither one of these is grams per meter squared, but what we want to do is do some units conversion to get it to the fundamental unit, and then back calculate which one of these 4 processes. We got to make our model match the data. And first we get the data and we say, wow, if it's 5 tons per hectare, what are reasonable values for these? So let's do, oh, we got one other thing I gotta show you too. This is one of my favorite test questions. Can you see that?
Oh my goodness.
That talk about yields going up. Can you see that from the video? World record pumpkin. This is a big contest. It had only started about 20 years ago. World record biggest pumpkin. We'll come back to this, but I gotta show you every single year. Here's a couple and they're giant pumpkin. They're just, these things are just giant. And they have to bring them in a basket and a forklift. They're up to like 2,000 pounds per pumpkins. And breeders are trying to get bigger and bigger pumpkins. And every single year the world record has been broken for recent years. And it's around a ton. One pumpkin weighs a ton. So my test question that I love to ask is, John and Harriet Smith grew a 1-ton pumpkin in their backyard, and they only have a backyard that's 10 feet by 10 feet. Could they possibly have grown that pumpkin in their backyard, or did they cheat? Did they give it steroids and hormones, which are banned in the world of pumpkins? You can't use steroids to get a giant pumpkin. That's a picture of it, and this is just mass of the pumpkin. And now we're up to 4,000 kilograms, and the line's still going up. It's just amazing. That's I've thought about doing a giant pumpkin in my garden. Put it on a balance, and people could come by and have a big digital display. Every day they could, yeah, yesterday that baby was 1,400 pounds, and because its balances are so sensitive, the digits would increment every few minutes. It would be, but it's all water too, by the way. this is all dry weight. But there's another case of pumpkins. Let's do the conversions, and there's 2 handouts here. For those of you that are here, there's one. There's a bunch coming by email. Conversion factors for your units. I just worked this out. Now let's go a little bit smaller. I think we can get most of this on here. First of all, this T for tons is a metric ton. There's a lot of weird units in the world. So this is a MT, and a metric ton, a ton is 2,000 pounds, but a metric ton is 2,200 pounds, or 1,000 kilograms. So 1,000 kilograms, we just call that a metric ton. Now what we should call it in SI units is 1, not megaton, 1 mg, 1 megagram. And if we just use that, everybody will know what we're talking about, but it's a metric ton. How big is a hectare?
100 by 100 meters.
It's 100 by 100 meters. Meters. Remember our first homeworks in centimeters per square foot? This is 10,000 meters squared per hectare. And remember how everything shifts by factors of 3? This one is a factor of 4. 10,000. So, but learning how to do this is like being bilingual. You can talk to everybody in the world about yield and get everybody on the same page. So here we end up with 10 to the 4th meters squared per hectare. And this right here in the denominator is 1 megagram is 10 to the 6th grams. So 10 to the 6 grams, this comes out to be 5 times 10 to the 6 grams per 10 to the 4th meters squared. And so 5 metric tons per hectare is 500 grams per meter squared. Now, we have day in here. The rate matters because the input is per day. These numbers are all per season, per year. And the goal is to get as high a yield as you can per year. As a rule of thumb, what I always do is assume 100 days growing season per year. And that's a pretty good assumption. If you get your crop planted by Memorial Day and you harvest on Labor Day, you're around 100 days season. Now, to refine this model, you could say, I think I got 110 days and da-da-da-da-da. But this is 500 grams per meter squared per 100 days, assuming they got this. The growing season was a little over 3 months long. So this is 5 tons per hectare is 5 grams per meter squared per day. Pretty convenient, huh? We get 5 here and we get 5 here. So, assuming I didn't make any math errors just now, this is these conversions. And bushels per acre, bushels is a unit of volume. Whoa! What does volume have to do with this? I guess before the days of electronic balances or something, people just did volume, and that's it. So we still do volume. But here's metric tons, here's megagrams, 100-day life cycle. 1 bushel per acre is about, if it's a 60 pounds per bushel, put that up here. Most crops are about 60 pounds per bushel. They really range from kind of 55 to 65, depending on the density of the grains. But 60 is a good average. You can look up this number on the internet for every single crop, and they're in this ballpark. So if it's 60, 1 bushel per acre comes out to be 6.7 grams per meter squared. And the bottom of this handout walks you right through all these conversions to get everything, shrink it into our common denominator units. Then there is the next handout. Now let's take this and look at, I'm going to put this up way over here. The next step, psychometric chart, we can erase that. If we look at some potential yields, some record yields, not typical, but record. One of them is 16 metric tons per hectare. Remember he said 5 is average, but people have gotten, in a perfect case, up to 16. And we do the math in this handout, and that, here we have it. Guess what? 16 grams per meter squared per day. Again, assuming 100-day life cycle. So we're going to have to, wow, what did they get for each of these parameters in order to get 16 down here? And 200 bushels per acre. You do the conversions in that. The record corn, anybody know the record corn yield? The world record corn yield. It's in the Guinness Book of World Records. It's something like 400. I haven't looked it up lately, but it's enormous. But if you could get 200 bushels, the people in the Corn Belt in the United States, they're getting 200 bushels an acre. This comes out to be 13.4 grams per meter squared per day. Look, these two numbers are pretty close, really different units, but they come out to be pretty simple stuff. Now, let's take our model and we're to actually simplify this so we can calculate yield. This handout, I have typical on the right side. Rate photon capture, let's start by assuming that was still 50% photon capture. That's pretty typical. Now, so far this number right here has been energy efficiency of photosynthesis, but to simplify this model and to get to the units we want, we're going to skip all this math over here where we had to go from quantum yield to energy efficiency. We can just put the quantum yield right here. Quantum yield, that's still an efficiency. And now the units are going to be moles of carbon fixed per mole of photons absorbed. And I've written that up here before. Let's take, what did I assume in this handout? 0.055 quantum yield. I should do the quantum requirement on this. 1 over 20, this is dang close to 1 over 18. Ben, do you have your calculator? Do 1 over 0.055. I think it might be this number right here.
1 divided by 0.055.
0.055.
18.18.
Okay, pretty close. This is about the quantum yield of 1 over 18 or the quantum requirement of 18. So these are a little bit stressed, but there's hot days in the field. But look what happens. We have moles of photons. This is dimensionless radiation capture. Moles of photons up here, P. Moles of carbon fixed. All of a sudden, we're at moles of carbon fixed per unit area per unit time, just by multiplying these three numbers together. And in this handout, which I will put right here, see if we can follow along with this column. We multiply these together, and did I assume we're doing this right-hand column, 50 more realistic inputs. In this, the realistic's on the left, and on the handout it's on the right. But I assume not every single day is perfectly sunny, so let's assume 50, and this becomes 2.97 moles of carbon fixed per meter squared per day. Now remember, that mole of carbon is going to become a mole of carbohydrate, and we can get a weight very quickly from this. Respiration efficiency, I assume 0.6. Oop, I'm wrong. This number right here, you multiply these together, and it's 1.38 moles of carbon fixed. Now we take it times respiration efficiency, following the handout, and it's 0.8825. And now we take it times harvest index, and I assume 0.4. So we end up with, instead of an energy efficiency down here, we end up with 1.38 times 0.6 respiration, we end up with 0.825. Oh, I did the math. I'm gonna handle this later. This is 0.825 moles of carbon per meter squared. How much? Where are we gonna put this? 1 CO2 goes to 1 CH2O. Quantum yield is carbon fixed. This is 30 grams per mole. We've done this math before. So we take moles of carbon fixed times 30 grams per mole, and all of a sudden now we have a weight, the weight of yield from quantum yield, respiration efficiency, and the number comes out to be 25, to match this, I gotta erase this, 25 grams per meter squared per day. That's weight here on the handout. And way higher than these, but we didn't do harvest index. Carbon partitioning efficiency, if we assume 0.4, real typical, now we're at 10 grams per meter squared per day of a potentially achievable yield, assuming these inputs right here. And look, the rice at 5, that was only 5. It shows you the potential for agriculture. With reasonable inputs, we could double that to 10. The beauty of this is you can take a yield and say, what values of these 4 components did we get to get that? If you have to, when we have to make measurements and models match, we say, wow, they only got half of our model, therefore quantum yield must have been a little less, radiation capture must have been a little less, harvest index must have been a little less, and if we inch these down just a little bit, all of a sudden we end up to match 5 grams per meter squared per day. Harvest index is common to measure. Some of these are not difficult to measure. Photon capture not difficult to measure in the field, and in fact, we measure that from remote sensing. Satellites flying over looking at the field, they predict yield based on photon capture halfway through the season. So some of these we can do in real time, and then this, of course, we can do at the end of the life cycle. So here's 10. Look at that. 10 is less than these numbers. So good growers are getting higher yields than our model. So sometimes our model over-predicted the typical yield. Here I had 160 bushels per corn, here's 200. You can see how we go back and forth between measured yields, units conversion, and the model. I don't think I'll go through this, but look at this. Model potential yield. In every case I put real good estimate. I assume 90% photon capture, but over here I still assume quite a low quantum yield. These are still plants that are a bit hot. Slightly higher harvest index. All of a sudden that 10 went to 27 grams per meter squared per day, just by tiny tweaks of these numbers. I might have started this over, but I'll keep it up here. But the key thing to remember in here is the second parameter is not energy efficiency anymore, it's quantum yield. And the units work out to go from photons to moles of carbon times 30, we have a weight of yield. And this is what we call modeling from first principles, right from quantum yield to the potential yield in the field. to be able to see this. I don't know that I need to give you this as a handout. This is some grams per, this is a table of the highest yields anybody's ever gotten in a short period of time. And this, some of this is rice, but some of it's stuff in wetlands, super high. Maximum growth rate in grams per meter squared per day. And look at there, 54, you can't see this, you gotta believe me. This is millet, remember millet C4, 54 grams per meter squared per day. Woo, that is smoking, that's higher than any of the numbers. But that was only for one day. In the peak of the season, and in the middle of the season, we're up to 95% photon capture, high values for all of these, and it was for biomass down here. These are not yield, they're just biomass. So people have analyzed this to death. Here's a key that, I'm gonna put this one right here. Remember our sigmoid curve of growth. Planting, harvest, and this would be grams per meter squared if we're doing this. Now, remember, what if we plot the derivative of this curve, and the fastest growth is right here. The derivative looks like that. So the blue line is grams per meter squared, but this line is grams per meter squared per day. And these record yields are the peak day right here. But it helps validate the whole model. If the peak, you gotta explain how you got the peak yield on a single day. So one's yield and the other one is yield rate. Let me close on how we're going to feed the planet. And we're in the middle of the COVID crisis, and you start to think, wow, how bad could things get? You know, we're not out of food, the grocery stores are restocked, but what if something happened? And you know what are our options for feeding the world? Why don't we just chemically synthesize food? We know how to do that. You just go to the biochemistry department and say, whip up some carbohydrates, get some test tubes going. They can do it. What's the problem with that? They just chemically synthesized carbohydrates. No agriculture. Why do we do that? Why do we have agriculture? Why don't we just chemically synthesize carbohydrates?
The inputs are expensive.
Yeah, real expensive. Way cheaper to use sunlight. There's an even bigger problem. From biochemistry, I think this is where you learn this, D and L rotation isomers. Carbohydrates and proteins have opposite rotation isomers, and we always say it's like your two hands, and they're the same hands, they just got the opposite shape. We can only digest one form of this. And I can't remember for sure, but I think it's D and L, and I think we can only digest the, which is my left hand, this one. It only digest the L rotation carbohydrate isomers. All biological organisms make 100% of the rotation isomers that we can use. If we chemically synthesize them, we always get a 50-50 mix. There's no way to make all L. So we've done rat feeding studies, and the rats get really sick when you feed them chemically synthesized stuff. They get digestive problems. So we cannot chemically synthesize carbohydrates and use them because we don't have any way to chemically separate those, even if it wasn't so bloody expensive. But the same thing's true for proteins too. When we synthesize proteins, we have no problem synthesizing them. It's just that we can't separate the rotation isomers. I think that's pretty interesting. Biological organisms, even bacteria, fungi, fungus, they make the rotation isomers that are good for all other biological organisms, and you try and do it synthetically and it's wrong. We have to rely on plants to make our food. How about fish? Animal agriculture is bad, right? I mean, grow corn in feedlots and feed it to beef, and it's all over all the environmental footprint of beef. Why don't we just eat fish? We got a lot of oceans, but there's not nutrients in the oceans, and even if we doubled the world catch of fish, it's still only something like 5% of our food needs. So fish aren't going to do it. Maybe we could try to someday use the oceans to fish farm. And it'd be tricky because we fertilize them and then they get algae blooms. And but fish are not a good solution. How about algae? We had a huge project here at USU for algal biofuels for many years, from about 2005 to about 2015. That was for fuels for cars. And actually, the project ended when we wrote a report and we said, we are proud to announce that if we can do everything exactly right, we can get algal biofuels down to $15 a gallon of fuel. And they said, and they cut the project. But you're right, when fuel gets up to $15 a gallon, we'll be ready. But look, algae turns sunlight into fuel for vehicles, for cars. And they had to do each of these component things. This exact model that goes to algae. Here's the problem with algae. We have to enrich with CO2 for one. They're in water, and the diffusion rate of CO2 in water is so slow that we have to enrich. But we can get high quantum yields, and if we do it right, the photon capture is real high. Their algae respiration efficiency is pretty good. It's like 80% because they don't have to grow stems and roots, they just grow cells. Now we get to number 4. Algae are full of chlorophyll, which at high levels is toxic to people. They're full of cell walls, cellulose, we can't break that down. So you process algae into food, and the harvest index is less than 10%. So even though people take an algae pill a day, try to eat half your diet of algae. You can't do it. They have to be processed. So algae isn't going to do this for us either. So we got to grow food, and we got to analyze how to optimize the whole system for food. But this model is directly applicable to every single photosynthetic organism. Even if it was photosynthetic bacteria, they got to capture light, they got to fix carbon, they got to use the fixed carbon to make proteins, other things in the plant, and then hopefully the organism has a good carbon partitioning efficiency. I might have said this before, but I'll close on this. Of these 4 parameters, which 2 have we made the biggest gains in to explain the enormous increase in agriculture? Do I have a graph of that somewhere? You get the idea. Food yields have gone up incredibly, really since World War II. They just, boom, skyrocketed. The Green Revolution, huge breakthrough in yield. So we've analyzed this hundreds of times. Which 2 things have we improved?
The carbon partitioning and the photon capture.
Yep. Number 4 has gone way up, and number 1's gone way up. And in spite of working on this like crazy, all we can do is say, well, we've got 3 options for photosynthesis, and we'll choose different plants. We've not been able to improve this. And we've also not been able to improve respiration efficiency much either. It is what it is. The plants are already pretty efficient. Now, one of these 2 has been improved by plant breeding, and one has been improved by cultural procedures. They're both equally important for a dramatic increase in yield. Which one is improved by plant breeding.
Carbon partitioning.
Yeah. This is breeding, genetics. And this one is improved by plant spacing, better irrigation, the earlier planting in the season, cultural procedures. And roughly, both of these, you could say they've roughly doubled. And if this is 2 times 2, that's a 4-fold increase in yield. And that's where we're at. Now we're running out of options because our yields are already pretty good. But we still use this model to analyze it and get into things. We're almost done with photosynthetic efficiency. We may be completely done. The next topic is respiration efficiency. Understanding how efficiently plants, and for that matter, our bodies, can turn food into energy and everything else. So we'll pick that up next time.